Imagine a place where gravity reigns supreme. This is a black hole, a region in space-time where gravity is so strong that nothing, not even light, can escape its grasp. These cosmic abysses are formed from the remnants of massive stars. Stars are like cosmic furnaces, fusing hydrogen into helium in their cores. This process releases immense energy, counteracting the inward pull of gravity. However, even stars have a lifespan. As a star runs out of fuel, the outward pressure from nuclear fusion weakens. Gravity takes over, causing the star's core to collapse in on itself. This collapse triggers a supernova, a catastrophic explosion that can outshine an entire galaxy. What remains after this cosmic event is a black hole, an object so dense that it warps the fabric of space-time, creating a gravitational pull so strong that it devours everything that crosses its path. Gravity, the force that holds us to Earth, is the weakest of the fundamental forces. Yet, in black holes, gravity reigns supreme, warping the fabric of space-time to an extreme degree. The immense gravitational pull of a black hole arises from its incredible density. Imagine squeezing the mass of the Earth into a sphere the size of a marble. That's the kind of density we're talking about. This extreme density creates a gravitational field so strong that it distorts the very fabric of space-time. Time itself slows down as you approach a black hole, and the escape velocity exceeds the speed of light, making escape impossible. The boundary beyond which nothing can return is called the event horizon. Once you cross this point of no return, you are destined to be pulled towards the singularity at the center of the black hole, where all matter is thought to be crushed into an infinitely small point. Black holes, though enigmatic, are not one size fits all. They come in different sizes, each born from unique cosmic events and playing distinct roles in the universe's grand tapestry. Stellar black holes, the most common type, are formed from the collapse of massive stars. These black holes typically have masses a few times greater than our Sun, but are squeezed into a region only a few miles across. Supermassive black holes, as their name suggests, are true behemoths. Lurking at the centers of most galaxies, including our Milky Way, these gravitational giants can have masses millions or even billions of times greater than the Sun. Primordial black holes, a hypothetical type, are thought to have formed in the very early universe, shortly after the Big Bang. These black holes could range in size from microscopic to billions of times the mass of the Sun. Section 4. Peering into the abyss. Unraveling the mysteries within. What lies beyond the event horizon, within the heart of a black hole? This question has intrigued and puzzled scientists for decades, pushing the boundaries of our understanding of the universe. This question has captivated scientists and science fiction writers alike, leading to many theories and speculations. From the laboratories of physicists to the imaginative realms of writers, the mysteries of black holes have inspired countless hours of research and storytelling. General relativity, Einstein's theory of gravity, predicts that at the center of a black hole lies a singularity, a point of infinite density and zero volume. This singularity is where the gravitational pull is so intense that not even light can escape, making it invisible and enigmatic. Here, the laws of physics as we know them break down. The familiar rules that govern our everyday experiences cease to apply, leading to a realm where time and space are distorted beyond recognition. Some theories propose that black holes could be portals to other universes or dimensions, known as wormholes. These hypothetical passages through space-time could connect distant parts of the universe or even different universes altogether. However, these ideas remain highly speculative and have not been supported by observational evidence. Despite the allure of such concepts, the scientific community remains cautious, awaiting concrete data. Quantum mechanics, the theory governing the subatomic world, offers alternative perspectives. It challenges the classical views of black holes and introduces new possibilities for understanding their nature. Some quantum theories suggest that black holes may not have a singularity at all, but rather a region of extremely compressed matter governed by quantum effects. This perspective opens up new avenues for exploring the fundamental nature of reality. The true nature of the black hole interior remains one of the greatest mysteries in modern physics, a cosmic enigma waiting to be unraveled. As we continue to explore the universe, each discovery brings us one step closer to understanding these fascinating objects. Section 5. Architects of the Cosmos. Black holes and galaxy evolution. Far from being mere cosmic vacuum cleaners, black holes play a pivotal role in the evolution of galaxies, influencing star formation and shaping the large-scale structure of the universe. These enigmatic objects, with their immense gravitational pull, are far more than just regions of space where nothing can escape. Supermassive black holes, residing at the centers of galaxies, act as gravitational anchors, holding galaxies together and influencing the orbits of stars within them. Their presence is essential for the stability and cohesion of galaxies, ensuring that stars and other celestial bodies remain in their cosmic dance. The energy released as matter falls into a black hole can heat up surrounding gas and dust, creating powerful jets that blast out into space. These jets, traveling at nearly the speed of light, can extend for thousands of light years, impacting the interstellar medium and beyond. These jets can influence star formation rates in the galaxy and even affect the growth of the black hole itself. By compressing gas clouds, they can trigger new waves of star formation, or conversely, they can blow gas away, halting star formation in certain regions. Black hole mergers, cataclysmic events where two black holes collide and merge, release immense amounts of energy in the form of gravitational waves, ripples in the fabric of space-time. These waves travel across the universe, carrying with them information about the most violent and energetic processes in the cosmos. These events provide insights into the dynamics of gravity and the evolution of the universe. By studying gravitational waves, scientists can learn about the properties of black holes, the nature of gravity, and the history of cosmic events that shaped the universe. Understanding the intricate relationship between black holes and galaxies is crucial for unraveling the mysteries of galaxy formation and the evolution of the cosmos. This knowledge helps us piece together the grand puzzle of how the universe came to be and how it continues to evolve over billions of years. Section 6. The Point of No Return. Event Horizon and Spaghettification. The event horizon of a black hole is a boundary in space-time beyond which gravity's pull is so strong that nothing, not even light, can escape. It's a point of no return, a cosmic precipice where the known laws of physics cease to apply. As an object approaches a black hole, it experiences an increasingly stronger gravitational pull. This difference in gravitational force across the object leads to a phenomenon known as spaghettification. Imagine a hypothetical spaceship approaching a black hole. The side of the spaceship closer to the black hole experiences a much stronger gravitational pull than the side farther away. This difference in gravitational force stretches the spaceship like spaghetti dough being pulled and thinned, ultimately tearing it apart into a stream of subatomic particles. This spaghettification process is a consequence of the extreme tidal forces near a black hole, a stark reminder of the immense power of these cosmic objects. Section 7. Eyes on the Unknown. The Event Horizon Telescope and Recent Discoveries. Recent advancements in astronomy and space exploration have provided us with unprecedented glimpses into the enigmatic nature of black holes, confirming their existence and revealing their profound influence on the universe. These cosmic giants, with their immense gravitational pull, have long been subjects of fascination and mystery. The Event Horizon Telescope, EHT, a global network of radio telescopes, made history in 2019 by capturing the first ever image of a black hole's shadow. This monumental achievement was a significant milestone in the field of astrophysics. This groundbreaking achievement provided direct visual evidence for the existence of black holes and allowed scientists to test Einstein's theory of general relativity in extreme gravitational environments. The data collected has opened new avenues for understanding the fundamental laws of physics. Gravitational wave detectors, such as LIGO and Virgo, have detected numerous gravitational wave signals from merging black holes, confirming predictions made by Einstein's theory. These detections have provided a new way to observe the universe through the ripples in spacetime caused by these cataclysmic events, and providing insights into the population and evolution of black holes in the universe. By studying these signals, scientists can trace the life cycles of black holes and understand their role in the cosmic ecosystem. These discoveries mark a new era in black hole research, allowing us to probe the mysteries of these cosmic objects with unprecedented detail. The high-resolution images and data are helping to refine our models of black hole behavior and unravel the secrets they hold about the nature of gravity, space, and time itself. As we continue to explore, each discovery brings us closer to understanding the universe's most profound mysteries.